A challenge that you guys identified was when we were using our equations, and I would say something like the electric field is equal to Q1, K times Q1 all over D. And a lot of people were taking a look at the situation, and maybe we had a positive charge here and a negative charge, and I was looking for the electric field that happened to be halfway in between those two charges. And you were wondering which one of these charges are Q1 and which one of these charges are Q2 and things like that. So I would like to address that in this little session. So take a look at what we have here. The first equation that we have, Coulomb's law, K Q1 Q2 all over D squared. And we saw this equation used in a number of situations, especially when we had two charges, and I was wondering how much force was acting on one of those charges. The nice thing about this is that it didn't matter which one you called charge 1 or charge 2, because you can see that both of the charges needed to be used in this problem. So I could have Q2 times Q1 or Q1 times Q2, and I would still end up with the same force. Also verifying that the force acting on one would be equal to the force acting on the other, or that was Newton's third law. So the force on one is equal to the force acting on the other. But I think where the real challenge came in was when we had a third charge introduced. And I would ask you, what is the net force acting on this first charge? And you could say, well, shoot, we have three charges here. One of the first things you need to do is to actually label which one each charge is. Charge 1, 2, and 3. Now, in our equations, I can see that, yes, there will be a force acting on charge 1, so there will be a force acting on charge 1 caused by charge 2. This was called the on-by notation, and you could see that if I have the force on 1 caused by 2, I better have charge 1 and charge 2 in my equation. We also then said that there was a force acting on charge 1 caused by charge 3, because between every two charges there's going to be a force. So that equation would look like this, with charge 1 and charge 3 involved, divided by the distance squared, whatever that may be. So now I can see that I would have a second force, this time a repelling force to the left, because both charge 1 and charge 3 are positive, so I'm going to end up with this repelling force here. And then, charge 1 and charge 2 were attracting, so I ended up with an attraction force there. And now with these two answers, I would be able to find the net force. So when we're taking a look at Coulomb's law like this, or even if we were taking at the electric potential energy as well, this also involved both charges, Q1 and Q2, and this was just over D, but you were able to identify what the electric potential energy was because it didn't matter what you called charge 1 and charge 2. However, when we were looking at the electric field, or when we were looking at the voltage, you notice I said that was the electric field 1, or voltage 1, and the reason was because in our equation I said that is caused by charge 1 at a distance away from that charge, or the voltage was caused by charge 1 at a distance away from it. So you can see in my two equations, you can see that I have a charge producing a voltage and a charge producing electric field, because every charge produces a voltage and every charge produces an electric field. Taking a look at the more complex problem that we have right here, which one are you going to call charge 1 and charge 2? The complex problem with voltage. Let's look at a new situation. Here is an interesting problem. What is the strength of the electric field acting on the 12 microcoulomb charge if it's placed 3 meters from an 8 microcoulomb charge? And then as a follow-up, how much force would be acting on it? So this is going to be a good situation to take a look at. What do we call charge 1? What do we call charge 2? And things like that. As a general rule of thumb, the charge producing an electric field, I call that charge 1. or the charge producing a voltage, I would call that charge 1. Because in electric field and voltage, again, it really does matter which one you call charge 1 or charge 2. So for this problem, I would say that there are two charges. I would have an 8 microcoulomb charge and a 12 microcoulomb charge, and they are separated by a distance of 3 meters. Now they're asking, what is the strength of the electric field acting on the 12 microcoulomb charge? So if there's an electric field here at the 12 microcoulomb charge, then we need to know what's producing it. Well, if there's an electric field here, it must be caused by this charge over here, this 8 microcoulomb charge. So since this is a positive 8 microcoulomb charge, I know that there will be an electric field here at the 12 microcoulomb charge pointed to the right. Now if you are also wondering, well, shouldn't each one of these charges produce an electric field? You could consider that, sure, but how far away from this 12 microcoulomb charge is the 12 microcoulomb charge? And the answer is, well, it's 0 meters away. So if we were to take a look at the electric field 0 meters away from this, we would end up with an undefined value. So that's why there's no electric field here caused by the 12 microcoulomb charge. Now further away, you can see that each one would have a distance from that point, and so it would end up having 2 electric fields at that place. But there's only one right here, and that would be caused by the 8 microcoulomb charge. So since the 8 microcoulomb charge is the one producing the electric field, I call that charge 1. And as a result, the electric field then would be called electric field 1. The 12 microcoulomb charge, I would call that charge 2, since that is the charge that is sitting inside the electric field. And as a general rule of thumb, we call the charge sitting inside an electric field charge 2. So for our first question, we could say, what is the strength of the electric field acting on the 12 microcoulomb charge? Well, we're just looking for what is E1. And when solving this, I know I could go K times Q1 all over D squared. And the issue that I think was identified was, well, which charge is this Q1 when I'm looking for E1? And you can see now, according to my picture, I already have that established, that this charge is going to be the 8 microcoulomb charge, not the 12. So I could go ahead and plug in my values. 9 times 10 to the 9th times the 8 times 10 to the negative 6 coulombs all over the 3 meters squared. And that's going to give me my electric field strength. Now after I have that, the next problem is actually pretty easy. It says how much force would be acting on it. I could solve this two ways. I could go back to good old Coulomb's law and realize that I have K, Q1, Q2 all over D squared. And since I have charge 1 and charge 2 already established and the distance between, I could go ahead and solve this one for the force. If I have this electric field, I could also use a different equation. I could take a look and say, well, the electric field is equal to the force divided by the second charge. This one says if a second charge is placed inside of an electric field, then it would experience a force. And so once I have this answer, then I would be able to go ahead and take that, multiply it by the second charge, and then simply have my force. So you can see that there would be a benefit in using this, especially if I was asked to find what the electric field was to begin with.